This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 26. So we've been doing this for about 6 months now. Hope everybody's staying well out there. We got great presentation today from Steve Cobb, the Science and Operations Officer in Tulsa, and Joseph Patton, who's a research scientist at University of Maryland College Park. Title of the presentation will be Application of GLM Gridded Products during a severe weather outbreak in Oklahoma. Before we get started, just a few reminders that we are recording this. So if your colleagues aren't able to join us due to working shift or for other reasons, please check out the VLab afterwards and catch it then. There will be Q&A after the presentation. Please go ahead and put your questions in the chat room, and that will help us organize our Q&A after the presentation. If you're interested in being a future presenter, please get in touch with us. We'd love to hear new applications of satellite data in the field. And finally, if you're looking for training materials, whether they might not exist or you don't know where to find them, Brian Mata in the Office of the Chief Learning Officer can help you with that. We've got a great team developing those materials. Thank you to the Tower S team, David Blutis, Lee Byerly, OCLO, the GOZAR program, and JPSS for supporting the Satellite Book Club. Without further ado, I'd like to introduce our two presenters for this morning or early afternoon, depending where you are. Steve Cobb has been the SU at the Weather Forecast Office in Tulsa for the past 3 years. Prior to this, he was the SU in Lubbock, where he was introduced to the West Texas Lightning Mapping Array and first helped integrate total lightning data into the operational environment. Steve is also a member of the Total Lightning Working Group and GLM Science Team, where he provides the forecaster's perspective. He's joined by Joseph Patton, who's a faculty assistant research scientist for the Lightning Research Group headed by Scott Orlowski at the University of Maryland College Park. His work focuses on creating detailed training materials concerning operational use of GLM. Before joining Maryland, Joseph worked for 2 years as an operational meteorologist for the National Weather Service in Goodland, Kansas, and he has published research on the use of lightning mapping arrays and ground-based lightning networks in order to better predict lightning behavior. Steve and Joseph, welcome to the Satellite Book Club.
Thank you. This is Joseph. I'll go ahead and get started for us today. Steve will take on after I give a brief introduction here. As you can see on your screen, this is a virtual AWIPS machine, so it looks a lot like the cave you're used to seeing. And what we're going to do is we're going to look at how some of these GLM products are going to be displayed and arranged within Cave with this new RPM rollout that's coming, that's scheduled to be out later this month. So right now what you're looking at is the full disk GOES 16 or GOES East image. And we've got just a basic channel 1 visible satellite. But then we've also got these blue flashes are our flash extent density. So that's essentially like a flash count, how many flashes are occurring in that one little grid space. So first of all, I want to show you how these products are going to look. So in the satellite menu, first and foremost, we're going to have this 5-minute GLM flash extent density for GOES East and GOES West full disk. So those are going to be easy to access right up front. But if you go into the East and West by sector and then choose full disk for one of the 2 satellites, there will be a full GLM products menu. So you'll have 1-minute and 5-minute GLM flash extent density. So that's a count, basically how many flashes are occurring in that 1 pixel. Minimum flash area. So what's the smallest of all the flashes occurring in that 1 pixel? What's the smallest area? Total area that any one of the flashes has, and then total optical energy, which is essentially the brightness or how much literally how much energy is being received or observed by the GLM instrument. So that's sort of your brightness factor. All of these are available for East and West full disk, and we're going to have about a month transition period. Right now, you're used to having the CONUS or PAC-US PACUS regions, but we're going to transition to where all of them are going to be full disk within AWIPS. we've got, so if we want to pull up, for example, minimum flash area in addition to flash extent density, these are the standard color scales. Each one of them has their own sort of strengths and weaknesses. The minimum flash area is really good at observing strengthening cores within storms. The smaller flashes tend to be where you've got a burst of lightning activity that would be associated with strengthening convection. And the larger flash areas are typically associated with, say, stratiform regions or anvil regions of storms, that, or maybe even decaying regions of lines. So minimum flash area is good to get a quick visualization of which parts of which parts of an MCS or a QLCS are strengthening versus weakening before that may show up in either TOE or FED. But there are lots of advantages here for having full disk as opposed to just the continental United States. I'm focusing in here. This is a good example that we've got going on. This is our invest here, our tropical invest in the Eastern Caribbean. And so this is a good way to monitor some of the convective activity with the GLM that's outside the CONUS that could potentially affect U.S. interests. So that's one good application that we'll be highlighting. There should be an actual quick guide coming out that really hits home some of the important points for full disk, using full disk imagery here within a few days or maybe a week or two. But I just wanted to quickly show you. So that's what it looks like, and of course you're usually going to want to use this in conjunction with ground-based networks if you can. Let's see if this comes up here. Yeah, so I just had it. Yeah, so it's always good to have a total lightning picture. So use the GLM imagery products in addition to ground-based networks such as NLDN or ENI total lightning. So this just gives you an example of how these products are going to be arranged within the satellite menu on this new rollout. The full disk has many advantages. East versus west, usually about right here, about 103 degrees west is the delineation or the demarcation to where it goes west, starts observing more satellite in the western United States. And then once you get to about 103 degrees west, longitude, then it goes east, which starts observing more lightning strikes or lightning flashes to the east of that. So goes west will generally have better observations for, say, atmospheric rivers or the Pacific Northwest, storm systems coming over the North Pacific and in Alaska, and then also goes east will, like I said, have that capability of really focusing in on tropical Atlantic basin tropical cyclones, and then also many of our severe weather events, whether they're in Dixie Alley or the Southern Great Plains or Northern Great Plains. So it's not just an end-all be-all 103 degrees west. We'll have some more information coming about that soon. But I wanted to show you guys what that looks like for AWIPS. And we have a case study, an interesting QLCS case study that Steve Cobb is going to talk more about. So for now, I will hand it off to Steve.
All right, thank you, Joseph. I'm starting up my presentation here. There we go. All right. So as Joseph mentioned, the flash extent density product has been in offices for a while now and is best used really to monitor, as he said, the trends in the updraft intensity. An increase in the flash rates reflects really a strengthening of that updraft, and where there's more ice-ice collisions taking place, especially in that important mixed phase region, along with charge separations, it's really necessary for the lightning flash to occur. And as the name suggests, it's also helpful to see the overall footprint of the lightning, which can be useful for IDSS. The minimum flash area product is replacing what experimental offices have been seeing for the past couple of years, which was the average flash area. Now, this presentation I have is going to show the average flash area versus the minimum flash area, but there's very much similarity to them. The product really helps to pick out where those new updrafts, are occurring, and it's useful in both discrete and in linear systems to offer additional insight into the maturing updrafts. Along with the flash extent density, where an updraft is intensifying, you actually find the higher flash rates. The sizes of those flashes will also be relatively small when compared to the weaker convection, where the flash rates drop off and the flash sizes greatly increase. Flash sizes on the order of thousands of kilometers usually occur in the trailing stratiform region, per se, of a MCS. And finally, the Total Optical Energy is probably the most intuitive product. As Joseph said, it's really just the brightness of the flashes and the overall GLM scene. The long lightning channels in the trailing stratiform region of QLCS, where lightning flashes are most likely come to ground, are depicted by the Total Optical Energy. And as seen in this example here, the highest values of optical energy actually correlates very well to the highest flash rates and the smallest flash areas. So these three products all together provide a good overall view of the lightning behavior in convective cells and convective updrafts. So we're going to look at a case here from May of last year here in Oklahoma of a QLCS. And first, let's orient you a little bit with the 6-panel. The GLM products that we'll be focusing on here are in the lower right and the middle right image of this image, the middle right panels. I use something like this when I'm in the mesoanalyst at my office. The GLM paired with MRMS products, base reflectivity, in this case SRM as well, and especially other satellite products. GOES products are really helpful in monitoring the overall updraft intensity and the trends in the updraft. So here we're looking at a particular storm, in this case a storm moving from the southwest to northeast in this example. This is actually a 5-minute accumulation of GLM, along with which is updated every minute. You can see in these first two images that the flash rates in the bottom right drop actually from around 54 to 27. The flash area also increases. Well, this in general would suggest that the updraft, or at least this portion of the squall line, the updrafts within this portion are weakening during this time. Now, as we go forward in the sequence here, you can actually see the updraft or the flash area also drop, but more importantly, the flash extent density product shows a increase in flashes, indicating again that the updraft has begun to re-intensify. These images are actually about 10 minutes apart, so we've seen actually 10 GLM products in this time period, and we've had a couple of updated scans in the reflectivity as well. So you can see that the reflectivity actually increases along this line, and we're starting to see maybe the hint of a circulation beginning to develop as it moves into this white circle. Just again for reference, the white circle just north of this is where the city of Tulsa is. So this is one of the southern suburbs of Tulsa, where this QLCS is going to impact the area, and we're going to actually have a QLCS spin up here within this white circle. So this actually was repeated many times during this event, not only here with this particular event or with this particular part of the line, but in other parts of this QLCS as it moved across central and eastern Oklahoma. We saw an increase in flash extent density, which indicated an intensifying updraft, intensifying cell concurrent with the mesovortex, developing mesovortex along the line, and it actually, I think it actually helped to encourage or help to support mesovortex strengthening and tornadogenesis. In other cases, it produced some just some strong winds along that line as well. But what we saw in many cases here was something similar to this, where there was an increase in updraft intensity as depicted by the GLM concurrent with a feature in the line that produced some severe weather. You can see in this last frame here that the mesovortex is actually kind of surrounded here by actually not only the existing updraft, but a new updraft that's occurring or beginning to develop or beginning to strengthen to the south. So say this was a warning decision, we issued a tornado warning as this mesovortex intensified and tightened. If this were a warning decision, the GLM in this case would probably give you additional confidence that if this continues, that warning would need to be continued downstream, which it eventually was. Now, as mentioned, the average flash area in this case is what I'm showing, not the minimum flash area, but the idea is that you would see the smallest flashes, these yellow pixels along this leading edge associated with the highest flash extent density values as well. So here's another loop showing this actually ends about the time that the previous loop began, or previous images began. Here we see an isolated cell well out ahead of the advancing squall line, or in this case, a cluster of cells to the west. So what we see here in the bottom right, again, is the flash extent density product. You can see the colors changing from the dark and light blues to the warmer yellows and oranges, indicating, again, the intensifying updraft as the more and more ice collisions occur in that updraft around the turbulent eddies in the updraft, creating more smaller flashes, increasing the flash rates, if you will, associated with the intensifying updraft. So what we're going to do here then is look at this a little more closely. Now we've gone from a 6-panel back to a 4-panel here, where we're focusing just on these GLM products. The flash density is in the lower left, the total optical energy is in the lower right, and the upper right is the flash area, average flash area product. I have the MRMS's reflectivity at the lowest altitude in the upper left, along with the Earth Network's cloud flashes and CGs. So we'll step through this loop one frame at a time, focusing on these 3 GLM products. Notice that in the lower left that the flash extent density increases from something in the mid-teens to almost 100 flashes in a 5-minute period. Again, the GLM is noting here rapid increase in the lightning rate over a short period of time, what's we consider to be a lightning jump. Now, I've kind of been used to seeing these lightning jumps occur when you see a extended flash extent density doubling over time, going from, in this case, 20 to over 40 in a short period of time, in say less than 10 minutes, a 5 to 10 minute period. And research shows that this lightning jump commonly precedes the occurrence of severe weather up to about 30 minutes. And as you see at the end of this loop, the Wichita Forecast Office did issue a severe thunderstorm warning in anticipation of this cell producing some kind of marginal hail or wind as it moved into Kansas. So even though the average flash area in this case is dropping with time as well. The average flash area sizes drop from around 300 to less than 200 within this updraft core, and that's notable because at this time we've gotten somewhere between 50 to 90 flashes that's being averaged, and their sizes are still dropping, indicating there's an increase in the number of lightning flashes that's occurring within that intensifying updraft. So we'll go to the last example here. This is monitoring the lightning channel extent and the overall CG threat within the trailing strand-form region of this MCS. Here I've gone back to 1 minute lightning data versus the 5-minute image we saw before. In my experience, the 5-minute accumulations, even though they're updated every minute, can still mask important storm scale features and characteristics of multiple lightning flashes are combined. So in this case, the total optical energy shows a lightning path or lightning channel fairly clearly here, extending to the west from the main convective line. You see 2 areas that are colored purple, indicating that they're very large extent flashes in area, in size, well over 4,000 or 5,000 square kilometers. Here in the trailing stratiform region. Those are associated with the brightest optical energy flashes. And if you look in the upper left at the MRMS reflectivity, but more importantly, the Earth Network's cloud to ground flashes, you can see those cloud to ground lightning strikes actually occurred within that footprint of the highest total optical energy. So the CGs are well within that footprint of the brightest flashes along that channel as depicted by the optical energy. I think this has a clear application to decision support and messaging, because this event actually occurred on a Saturday morning where I'm sure many people were eager to resume outdoor activities or begin outdoor activities after the squall line passed through their location. There was still a fairly significant threat of cloud to ground lightning, hazardous lightning strikes, after the squall line passed. And the total optical energy, I think in this case, does a good job of depicting that channel and where those lightning, where that cloud to ground lightning would most likely come to ground. So some key takeaways here. GLM data is useful in monitoring the individual updraft intensities and trends. That's important to both the mesoanalyst and the warning forecaster. The information that you see in the GLM is useful in determining overall aerial coverage of that hazard, as well as helping to increase confidence when a warning decision needs to be made or whether a warning needs to be extended. The use of the GLM data that has the same trends with other multi-sensor data, such as the satellite and especially the radar, can give you that increased confidence. And the addition of these 2 other products, the minimum flash area and the total optical energy, I think provides a complete amount of information about lightning behavior throughout the whole spectrum of the storm types. And as shown, it's important also to have the ground-based networks paired with the GLM. That helps to remove that parallax and helps you be able to follow those individual updrafts as they move. So I'm going to leave it here with this loop of from last Tuesday of the QLCS that was moving through the Illinois area towards Chicago. I put on here the best I could the SBC storm reports. You can see there's a couple of swaths of wind damage that extended from Iowa across Illinois and even southern Wisconsin here. And those 2 wind swaths and even you see a tornado warning pop up here basically were co-located and concurrent with the GLM flash information. And this is actually the minimum flash area product. So you'll see, as opposed to the average flash area, there's a lot more of these yellow pixels indicating the smallest resolvable sizes, if you will, of these flashes within these individual updrafts along that line that are most intense. And that goes along fairly well with the bowing portions of the line, both in the upper portion of the line and in the middle portion where those severe weather events occurred. And that's all I have. Be glad to answer any questions or turn it back over to Jordan to facilitate the rest.
Okay, fantastic presentation. Thank you so much, Steve and Joseph, for being with us today. And Steve, particularly great synopsis of the use of lightning data in your presentation there. We have a few questions. I'm going to start with the questions, and then we'll wrap up for people that have to go at the bottom of the hour. And then if you're willing to stay on with us, we'll run through the additional questions that have come in through your presentation, if that's all right with you, Steve and Joseph. Okay, so one of the questions that we have is with regards to integrating GLM data at a field office with the terrestrial lightning strike data. A lot of forecasters have that ground-based network strike information up on their D2D throughout warning operations, and it's pretty easy because it's just point data. They can see the radar underneath it. But with GLM, as we've seen in these displays, it's a little bit different because you do have a plan view plot to look at. So just curious, Steve, from your perspective, maybe Joseph, from your previous work at a forecast office, how does that fit into the real estate that you have on the screen and the information that you're getting from it?
Well, I think that the GLM data needs to be displayed in a prominent way that also does not overlay or, as you say, hinder the viewing of radar data. So what I do, I typically put the GLM satellite data over other satellite imagery, and then have the radar and the ground-based networks in another pane, so I can match up the features that I'm seeing in the satellite data with the actual radar data itself. So you can actually load up several of these products. Like I said, I use the 1 minute data just as much as the 5 minute data with the 5 minute accumulation with the 1 minute updates, and I'll turn on and off those when I'm interrogating a particular storm.
Sounds good. Joseph, anything to add on that?
No, I don't. I think that there. I'll say a little bit. That there have been lots of experiments with forecasters in the houses with a test bed, which have showed that you really need all of these lightning sensors or detection networks in conjunction with each other to get the total or holistic understanding of what's going on there. You see that besides just the point-based things, which ground-based networks like ENTLN can bring, the GLM gives you so much more information about how strong a lightning flash is, how bright it is with its TOE, and what's the average, or sorry, what's the minimum size of the flash, which, like we've shown, gives you an idea of which parts of a storm or a convective line may be strengthening or weakening. So there's all sorts of information to be gleaned from. It's just it's another tool in the toolbox for you as a forecaster in order to get the most information you can with all the products available to you.
Okay, thank you. Well, let's just pause the questions for a minute here so I can wrap up for people that do have to head out. If you have feedback on the Satellite Book Club, there is a link in the chat now that you can click on. Just like everything these days, we're looking for your feedback. So please let us know how we can make this the best use of your time. I would encourage you, after you complete that feedback survey, to join us next week, Thursday, November 19th at 12 noon. We'll have John Evans and Lee Byerly from the Tower S team discuss the new content and updates in the Tower S RPM version 20. So this is going to be particularly relevant if you're a science officer or an ITO. We got the next version of the Tower S RPM, which brings those updates to AWIPS for satellite data. So look for an email from the Tower S team on that. So if you have to head out, hope you're staying well, and hope you'll join us next week. We'll go back to Steve and Joseph now with some more questions from the audience. All right, so our next question is for you, Joseph, comes from Scott Lindstrom, and it is, you mentioned in your opening dialogue that there was a longitudinal boundary at 103 for using goes east first goes west GLM data. So Scott's question, and I also picked up on this, is why is it 103 instead of 106, which is approximately halfway between the satellite subpoints at 75 and 137?
Yeah, I think that's an excellent question. If you do the math, it would appear that 106 would be exactly halfway between those two points where the two goes east and goes west satellites are currently positioned. There, I can tell you, I don't know the why, so to speak. I don't know the reason that ends up being the delineation, but I can tell you that that research has shown that for some reason that line at 103 degrees west is the line of latitude at which goes west tends to observe more flashes to the west, and goes east tends to observe more flashes to the east. So I know my boss, Scott Rudlowski, he's publishing a paper which has that as its as one of the as one of the tenets, where it's actually comparing the Go 17 and Go 16 GLM flashes just to get an idea of what's going on there. And while I saw your question earlier, and I scanned through the paper again just to see if he had any reasoning in there, and I couldn't find anything obvious, but they do make the point that mathematically, if you look at where more flashes are observed by one sensor versus the other, that delineation or demarcation is typically 103 degrees west. So I don't have anything to say about exactly why that's the case. I tried to come up with a couple reasons and I couldn't, but I can reach out to Scott Rudlowski and see if he has any conjectures about why that's the case.
Yeah, I don't know if Scott is with us on the phone, if he wants to weigh in. I see a Scott R, but I don't know if that's Scott Rudlowski. Okay, well, we'll try to follow up with that. That's an interesting finding there. Okay, a couple questions moving on here. Brian Curran asked about why using ENTLN over NLDN data, and Dan Lindsay was wondering, I think Joseph, you covered a little bit of this earlier about the extra information GLM provides on top of what you get from ENTLN. So when we have all these different data sources, what's the independent value of each one?
I'll take the first part of that, I guess, from Brian. It's actually not either or, it's both. I use ENI as well as the GLD 360, which provides you the total optical or the total lightning information from the NLDN or that network, the VISOLA network. One network may correctly may miss some of the flashes. I know Jason Jordan, I'm sorry, has done a lot of work showing how different flashes are seen by different networks. They may misclassify a flash as a CG versus a cloud flash. So I use both of those networks concurrently in my display as well, just so I get a good view of the total lightning going on. One thing that you have with cells that are deep cells and the lightning flashes occur lower in the cloud or lower in the storm is you can have optical extinction where that light actually does not make it up to the cloud itself. And you can use that to your advantage when you're looking at a ground-based network. Say that the GLM data shows a rapid decrease or a marked decrease in the lightning rates, but there's really no equal change of strength in the updraft itself as viewed by radar or even the ground-based networks. That can tell you something important about that cell, that it's really loaded probably with a lot of ice and cloud liquid water content, and it's potentially more significant than the GLM is showing you at that point. So using all that data together, ENI, the NLDN or GLD 360, all provides you, I think, important information about the total lightning behavior within updrafts within cells that can give you good lead time on their occurrence of severe weather associated with them.
Okay, thank you. Our next question comes from Scott Lindstrom. He's wondering, and I think there was some capability that was discussed very early on in when GLM was being evaluated in the hazardous weather testbed about an AWIPS plugin that allowed a storm anchored meteorogram. So you can see things like flash extent density or other fields, their evolution over time without having to sample every individual frame. Is that something that is still being worked on? Is it available in the field? Is it something that's being routinely used in operations?
There currently is not in AWIPS an ability to quickly look at a meteorogram behavior of a storm. There is the feature already available in AWIPS that you can look at that, but it does take a lot of work to do that. You have to actually go frame by frame. You have to put the cursor over the area that you want to sample and then move that frame by frame, and it'll give you a decent meteorogram. I've used that in research and looking at particular events, but real time it's just not practical. It would be really nice to be able to click and drag and put an object maybe on AWIPS and then get a quick readout of the information, that the GLM information underneath that object would be great, kind of like the Prob Severe gives you. It'd be nice if we had a intuitive way of doing that and user-defined way of doing that versus having to just sample individual pixels, pixel by pixel, and then put that picture together kind of in your mind about how things have changed and how it would look in a meteorogram.
Thanks, that's a good recommendation. I want to switch now to a couple questions from Bill Line. The first one I'm actually going to answer courtesy of some feedback that I've received from the Tower S team. And Bill was wondering, are there plans to include 10-minute GLM products to match the cadence of the full disk ABI imagery? And we had Joe Zajic help me with this one. He said that initially we were feeding the 1 minute and 5 minute average to the field, and that matches again with the CONUS cadence. Or ABI CONUS cadence, I should say, and our intent is to push the averaging out to the AWIP systems so that other offices can tune the window size and update rate to how they wish. And again, we're still working on some of the practical details such as bandwidth and latency of doing that. That we're also going to be experimenting with the Aviation Weather Center on 10-minute averaging, since they have a much larger AOR. I'm sure Pacific region would also be interested in that. So if you have specific questions about averaging schemes and whether 1, 5, 10-minute work best, we have a cloud system now that we can use, and I think our Tower S team would be happy to work with you. So if this is a topic that's of interest to you, Bill, or anyone else, feel free to get in touch with us, and we'd love to engage with you more on it. And then one more question from Bill Line to our presenters for today. Have you experienced or seen a situation where Total Optical Energy provided information not available from the other parameters that influenced operational decision making, particularly with regard to cloud to ground potential? Bill says he thinks a forecaster should communicate CG potential with any lightning activity present per the flash extent density.
That's a really good question. The total optical energy kind of gets overlooked sometimes, I think, and is not appreciated. And as I showed, the ability to actually see the lightning channels within a trailing stratiform region, or even forward stratiform region ahead of a developing supercell or something like that. I know that Bill Koschak has done some recent work correlating millions of GLM flashes with hundreds of thousands of ground-based network flashes, NLDN, I believe, and he found that GLM ground flashes, of course, are optically more energetic than the cloud flashes, and ground flashes actually have a higher peak current. So there's some application, I think, there is still some work to be done and some refinement of that, but there's potential for, like Bill is suggesting, noting maybe where you have some continuing current and potential for fire starts and that sort of thing. So I think that the Total Optical Energy offers maybe a insight into where it's most likely to see those flat ground flashes come to ground.
Okay, yeah, very interesting. And how does a very tall convective cloud or the location of a flash deep within the storm impact the GLM products?
Well, a deep convective cloud usually has a lot of hydrometeors. That is actually not what does much of the scattering that's found in some of the more recent research that was shared during our GLM science meeting. It's not those precipitation sized particles, but it's the overall cloud amount of cloud water or cloud water path that scatters the light away from that scatters the light or attenuates the light where it does not reach to the top of the cloud and the GLM sensor does not see it. And of course, what goes along with that is also large ice particles within the cloud. So it's actually the amount of the quantity of those in the cloud itself, not necessarily the precipitation that does much of the scattering of the light is kind of what the latest research has found. So if a lightning flash occurs, and GLM typically will miss some of the smallest flashes, but if a lightning flash occurs, a small flash within the core in that updraft, on these eddies of the updraft, if it's deep within the core and low in the cloud or low in the storm, there's an opportunity there for that light to be scattered or attenuated and not reach the sensor. So what you'll see then is a lessening or a lowering of the flash extent density, a lowering, of course, of the amount of optical energy, the TOE, the total optical energy reaching the satellite. So it'll mute in some ways, mute the results that you see at the satellite level. These values will be lower.
Okay,
and I just wanted to add there right quick. You know, the GOES 16 or goes east and the GOES 17 goes west, they have a significant overlap in terms of their field of view with the GLMs over, honestly, much of the continental United States. So we've talked previously about 103 degrees west, but it's not that simple. Like Steve was mentioning, there are many things to take into account, including, you know, just think about as a forecaster in an operation, working in operations, what may be attenuating or blocking all of the light from a particular flash from reaching this satellite-based lightning imager. So even if you're working at a severe weather event in the central United States, in the Great Plains, it still may be a good idea to have both GOES 16 and GOES 17 GLMs at the ready in case one, for any particular reason, you know, whether it's the path that the light has to take is being scattered by a lot of hydrometeors or cloud particles, for whatever reason, that central United States region where a lot of severe weather occurs, especially if we're talking closer, a little bit further west, closer to the high plains, you're going to be right on that line. So you're really going to want to have both at the ready. It's not always going to be clear cut which one's doing better. And it may not always be clear cut which one's doing better from frame to frame either. So that's another thing to take into account.
Okay, thank you. And just to follow up on that, we did get a comment from Scott Orlowski in the chat that said that the GLM full disk quick guide will illustrate the width of the boundary between GOES 16 and GOES 17 for some of the earlier discussion we had, and the instruments perform relatively the same between between 103 and 106 degrees west, with of course GOES 16 better to the east and GOES 17 better to the west. Steve and Joseph, thank you so much for being with us today. I really appreciate your presentation. I think probably everybody else did as well. Very relevant and good questions and answers to those at the end as well. With that, I'll wrap it up. I hope everybody's staying well. Hope you'll join us next week. and take care until then. Bye now.